Okay, yeah. So thank you very much. I'm Michael, and I've got Sami down here in the audience somewhere. So we're from the University of Saskatchewan, and this project was in collaboration with Agriculture and Agri-Food Canada. So I'm going to talk to you today about how to improve streaming video, and in particular, how to make it easier for people to do a task called early navigation using a new technique that we call SpreadFrame Loading. And here's what I'd like you to remember today. The problem that we saw on this project was that when video overviews load slowly, users have to wait to navigate. So as you can see in this example, there's actually an implicit bias here. This technique assumes that the content the user wants to access is more likely to be close to the start of the video. So if these yellow bars are the frames of the overview, and we know we want to go to the spot in the second half of the video, we have to wait a long time before being able to see what's going on in that second half. And the solution that we came up with is to change how those overview frames are loaded to spread out coverage across the whole video. And when we spread out the frames, we get access to the entire video, first at coarse granularity, and then it gets finer and finer as it fills in. So here is a head-to-head comparison, and you can see that if we want to navigate to a place in the second part of the video, before the regular overview even gets to halfway, we already have a fairly good coverage of the entire video down at the bottom. So here's what I'll cover today. First, we'll go over the basics of streaming video, and I'll tell you about the task of early navigation. Then we'll talk about why early navigation can be difficult when overviews load slowly. Then we'll go through spread loading, our solution to the problem, and then I'll cover the study we did to evaluate the technique. But first, this presentation is brought to you by canola. This is an agricultural test plot of canola, which is a great Canadian invention that is now a big crop in Canada and a big research area. And we've been doing work with time-lapse sequences of canola growing out in the field. So this is one of our crops from June through July, based on a picture taken every minute over those months, with some gaps. Other data sets that we have would cover the entire growing season from May through September. And this is what we'll be using as the basic kind of video that we want to stream and that we want to navigate in. So let's now take a quick walk through the history of web video. In the old days, the entire video downloaded before playback. Perhaps you remember old flash animation screens. These were incredibly slow to load. For all you know, this might be an animation. This was so slow that animators began including simple games in the loading screens to keep viewers from leaving. Then streaming video came along, which was okay for playback, but what if you want to move to a different location in the video? Well, you'd have to click on the seek bar to change the playback start, which is great, but how do you know where to click? So in 2012, Matejka, Grossman, and Fitzmaurice showed that it was really valuable to send a low-resolution version first, which is now common as a thumbnail overview shown when hovering on the seek bar, as you can see here. This allows moving back and forth on the seek bar to find a location to click and change the load point. And that is the task of early navigation, using the thumbnail overview to quickly find a location so that you can click to change the load point of the main video, without having to wait for the large version to download. So overviews were a solution to the problem of slow loading video. But we asked, what if the overview also loads slowly, too slowly to do early navigation? Here is an example. And this is on a desktop machine and a broadband connection, but using the Tor browser. And you can see that when the overview is black, it's because it hasn't loaded yet. So if I want to navigate around in the video by searching on the seek bar, it takes a long time before I can do it for the second part of the video. And eventually, when the entire video is loaded, the entire overview is loaded, I can choose the location that I want to start playing. So you may be thinking to yourself that in most cases, this isn't a problem, that overviews usually load pretty quickly. So let's have a look at when this problem can occur. Here's a trade-off chart that shows how long it takes to load a 200-frame overview, where the different lines show different frame sizes, and the x-axis is our network bandwidth. And the trouble zone for a user would be anything above about the 5-second mark, particularly for larger overview frames like the yellow line on top. Now, if you're like me, you might be looking at this and thinking 1 to 10 megabits per second. That seems a little slow. How realistic is that? Well, let's take a look. So these are global average internet speeds by country in megabits per second. And you can see here right away that vast regions of the world have an average bandwidth of less than 5 megabits per second. Now, even if you have a faster connection, if you're sharing the connection with other users, for example, friends or family members, you might only get a portion of the available bandwidth. Or perhaps you're a single user with a lot of active processes across several devices, each using up a portion of your bandwidth. Or, as you saw earlier, various tools for enhancing privacy, such as the Tor browser or VPNs, can slow down download rates. So this shows that it is realistic to encounter the bandwidths shown here, and we should be taking the users who have those kind of bandwidth speeds into account, not just those with the latest technology. But what about frame size? Do we really need 25 kilobytes for an overview frame? So this takes us back to the agricultural context, where we were using these time-lapse videos to look for points that correspond to very specific growth stages in the crop. For example, the start of flowering is an important event, and we need a lot of resolution to be able to see that precisely. So to demonstrate, I want to ask you a question. Is this plot flowering? This image has been compressed to 1/9 of the original size and is approximately 28 kilobytes. And if you look very closely, you might see some hints of yellow in a few places. For example, here and here. But are those really flowers? Or are they just bright reflections off of the leaves? Or perhaps something else entirely? At this resolution, it's difficult, if not impossible, to say. So now here is the full resolution image. You still have to look very closely to make out the flowers, but they are at least distinguishable. But if this is a frame from a 4K video, it's about 256 kilobytes, even with compression, way more than that 25 kilobyte line that we were showing earlier. So for different tasks and different data sets, there are definitely situations where the size of the overview can cause us to get into this problem zone. And since one of the use cases for us is being able to access high-resolution data from out in the field on a rural cell network, we have the problem coming at us from both sides. Okay, so the main thing that we saw that prevented people from being able to do early navigation was that the overview loads linearly from the start, which we call linear loading. You've seen this demonstration of the idea, and here is an example of it in our Timelapse Viewer. A couple things to point out here. Our videos were up to 100,000 frames each, and instead of using thumbnails on the seek bar, because they're actually trying to pick out details in the video, our player filled the view with the overview. And then when you clicked, it would go to the higher resolution version. There is a better version of the linear technique, though, where you can click wherever you want to change the load point, as you can see happening here, which is what you're probably used to from video players. Okay, so as you've already seen, our solution to the problem is to spread the frames out as they load, to maximize coverage in order to try and support early navigation. The basic algorithm is simple. Order the delivery of the overview frames so that you always fill in the largest gap. So we load the middle frame, then the first, then the last, the frame at 1/4, the frame at 3/4, and so on. And here's what it looks like in our Timelapse Viewer. It's worth noting here that this idea does work particularly well with time-lapse series because of the general consistency of the scene, but we do think that this technique would work well for other kinds of video. So here's a summary of the techniques that I just showed you. You'll notice that we did also have a condition where it was possible to change the load point by clicking in the spread loading case, but you'll see later in a bit that it really didn't make much difference. So these were the 4 conditions of the evaluation that we did to test the effectiveness of spread loading. And the task was to locate a specific scene in the time-lapse series. It was within participants, and we simulated a slow network. Here is what the study looked like. The target will appear on the right. Again, their objective was to find the target moment in the data set, plus or minus approximately 30 minutes. Across the top, from left to right, there were low, medium, and high resolution tabs, each representing a smaller time scale as the resolution increases. So the low resolution tab would cover the entire season, and the frames in the high resolution tab would be generally 1 minute apart. So at that point, you're only getting a few hours of coverage. Participants would have to navigate through all 3 tabs to complete a single task. So here's the study in action. There were many similar-looking moments in the data set, owing again to the general consistency of the scene. We put hint boxes in the lower left as an idea, the idea being to simulate the kind of expert knowledge that agricultural researchers might have that would allow them to distinguish from otherwise apparently similar scenes. So you can see that here as the yellow square. And these would suggest to the participant that they were within the relative vicinity of the target, but they were not precise. So participants would still have to analyze the target image to find uniquely identifying features. Carrying on, you can see that the participants would have to use all three tabs as part of the task. The size and color of the hint boxes, as you'll see in a moment here, were dependent on which tab they were in to help to distinguish between the three tabs. Once they get within 30 minutes of the target frame at the high resolution tab, as has happened here, they can verify their selection. So the task consisted of navigating from an overview of the entire growing season down through smaller time scales and higher resolutions, homing in on a target frame. And here are our results. Spread loading is in green and linear loading is in blue. You'll see that spread loading was significantly faster and click seeking had a relatively small impact on performance. This came as a bit of a surprise to us. We thought that it would be much more helpful. And in some cases, we actually observed in the linear with click seeking condition that participants were effectively simulating the spread loading technique by clicking around the seek bar. But it turned out that they weren't very efficient at it, which is why spread loading was faster. It's also interesting that the ability to click to change the load order did not significantly improve the spread technique either. So that means it's perfectly fine for it just to be automatic. And of course, note that the completion time there is actually in seconds, going all the way up to 80 seconds there on that bar. So in the linear mode, the task took more than a minute to complete per target. And spread loading was able to shave about 20 seconds off of that time, which is a significant savings, especially if you're doing many of these tasks throughout the day. So here are the scrubbing time results broken down by tab. Scrubbing refers to dragging back and forth on the seek bar. Remember again that participants moved through all three resolutions, low, medium, and high, to complete a single task and could switch between the tabs at will. They could even go back up to a lower resolution. You'll see that significantly less time was spent scrubbing for spread loading in both the low and medium tabs, but you can see that at the high resolution, linear seems to take the same time as spread or less. And this was actually because users would get so frustrated when they first got to that tab and didn't see they'd found the target, that they actually preferred to jump back up to the medium resolution and start searching around to try a different point, which is also partly why you see more time spent in the medium tab for linear loading. So some takeaways from all this. Spread loading works very well, and there's not really any penalty for fast networks, as in that case, all the frames would load so quickly that there's effectively no difference. So that being the case, we would recommend using spread loading as the default technique for loading overviews. Now, with a bit of video processing, this technique can work with video codecs such as MPEG. Generally, if you can pull out overview frames using keyframes or iframes, whatever you have for your codec, you should be good to go for spread loading. Now, one thing is we used uniform sampling for our study and application, as our use case is specifically to help researchers find the interesting points in the video. But with other video formats such as movies, it may be possible to use non-uniform sampling, for example, by using scene transitions, or by tracking user activity to find the commonly accessed segments of the video. Now, we did think of one potential anti-use case. If a user is following a scene until some particular event occurs, spread loading may not work. But you would note that if that scene is in the second half of the video, again, you run into the same problem with the linear technique, where they still have to wait. One way around this problem may be to adjust the load sequence according to user activity. So if they're dragging around in some area of the seek bar, you could load the overviews in that vicinity first. So here's our take-home message. When video overviews load slowly, users have to wait to navigate. But this problem can be overcome by changing the load order of the overview to spread coverage over the entire video at all times. Thank you.
So, any questions? Fabrice Matulik, Preferred Networks. I really like how you motivated your problem and how you made it very clear why this is useful. So you mentioned one way you can make it a little bit adaptive. I could think of another way also of making you mentioned the resolution problem, but you could also accelerate the loading by having first loads of low-resolution images coming up and then having a multi-pass or a multi-resolution approach where, first you have the low-resolution images loading very fast, and then if the user is interested in a particular area, they would dwell on an area, and then like progressive JPEGs, they would load progressively. So I don't know if you consider these options of using, multi-passes and adaptive previews and things like that.
It sounds roughly like what we ended up doing for the tool that we delivered to researchers, where they would have that first low-resolution overview, and then they would, once they select an area, it would load a higher resolution from that point, just kind of close to that area. But we can look at making it potentially more dynamic and adaptive too. Thank you.
Hi, Sean Cross from UC San Diego. First, thank you so much for this work. This was a great talk. This is I just really enjoyed this work. Something that I was thinking about was, so much infrastructure and thought has been put into content development networks and to their architecture and the infrastructure that goes into them in order, based on behavioral data, based on the fact that, Netflix wants a particular show to be able to start at a particular time for a customer, and if it doesn't start within like a certain time window, well, they might go to something else, or Amazon Prime or some alternative. And so I was wondering if you've thought about the extent to which this kind of a loading scheme fits into all those algorithms and infrastructure that have really been optimized for content delivery.
I think it would fit. Because they're already loading sending overviews over the network, and really all they have to do is they'll have like some queue by which those overview frames are sent, and really all we're saying is just reorder that queue, and that'll actually be of a benefit to the end user. So there's no reason why this shouldn't be able to fit in existing networks.
So thank you. It's really interesting work. I'm curious, did you test this at all on mobile phones? Because, on mobiles we touch. We don't really hover.
Right. Yeah, but you would generally, I think you can still do the scrubbing task, though, on mobile phones, but you actually end up putting your finger on the screen and dragging around. And it should work just as well on the touch device. We did use a desktop for our study. But yeah, we want people to be able to use it on.
I guess you wouldn't want to even do this kind of task on a mobile phone, but yeah.
Well, you might be able to do it if they're out in the field with a tablet. We want to be able to support that as well.
Indeed. We have time for more questions. Okay, then please let's thank our speaker again.